Good afternoon, everyone. My name is Lucian Pullen, and I will be your tutor for today. Okay, I'm just doing some testing. Okay, it seems that the mic is picking up my voice. Okay, now today we are continuing where Arnold started on Monday. He started with conservation of energy, and that is what we will be continuing with today. Okay, so without any hesitation, hey, let's start with this problem number 6. Arnold ended yesterday with problem number 5. Let me just check that everything is streaming okay to the YouTube side of things. Okay, that's the tutorial. And everyone should be seeing what I'm seeing. Okay, so let's get busy. So the question asks, or rather tells us, the coefficient of friction between the block of mass M1, okay, which weighs 3 kilograms, and the surface in the figure is mu k, which is the kinetic coefficient of friction, is equal to 0.400. Now they tell us further that the system starts from rest. What is the speed of the ball of mass m2 equals to 5 kilogram when it has fallen a distance of 1.5 meters. Okay, so this is basically the setup that we have. Okay, I'm going to draw what we have, or what we're supposed to be showing there is we have a 3 kilogram block, as they tell us there. We have a surface, let's just say it's a table. We have a 3 kilogram block on the surface. It's a rough surface. We have a 3 kilogram block on the surface. This block is connected to a rope, which is connected to a ball. Okay, a ball which weighs 5 kilograms, they tell us. Now, you should by now realize that this block, due to its, this ball is going to pull the block towards the right due to its weight. Now, they tell us that the kinetic coefficient of friction, mu k, is equal to 0.400. And let me just rewrite that part. Mu k, the kinetic coefficient of friction, is equal to 0.400. And this block is going to start falling downwards. Now if I'm going to read the question again, you all have a visual picture of what is happening. So we have the coefficient of friction between the block and the table or the surface, and that coefficient of friction is 0.4. They tell us that the system starts from rest, and then the question they want to know, or the answer they want, is what would be the speed of this ball when it has fallen a distance of 1.5 meters. So after the ball has fallen a distance of 1.5 meters, let me just, so let's say this is the surface. This is the surface. It continues. This ball is obviously going to fall. The ball is going to fall downwards. And they want to know what would be the speed of this ball if it falls a distance of 1.5 meters. Okay, what would be the speed here? Obviously, it's going to pick up speed because it started from rest, and the gravitational acceleration is going to cause it to accelerate. So what would be the speed at this point after it has fallen a distance of 1.5 meters? Okay, so now that we all have this picture in our minds, some things we need to know. First of all, that this is a closed system, so the change in the kinetic energy plus the change in the potential energy plus the work done is going to be equal to 0. So according to the law of conservation of mechanical energy, which I'm just going to short to ME, the conservation of mechanical energy, which I'm just shorting to ME. And let me just see if there are any questions, comments, what have you. So the conservation of mechanical energy, that means, according to this law of conservation of mechanical energy, that the change in the kinetic energy plus the change in the potential energy, let me just write it as PE, I prefer PE, potential energy, plus the work done by an external force is going to be equal to 0 according to the conservation of mechanical energy. Okay, this all will be equal to 0. Change in potential energy plus the work done by an external force equal to 0. Now we know that the change in kinetic energy is just the final kinetic energy minus the initial kinetic energy, plus the change in potential energy is just the final potential energy minus the initial potential energy, plus the work done by an external force. Now the external force in this case would be the friction, so basically the work done by friction, so it's the force of friction multiplied by the distance, and that's going to give you 0. Okay, that's according to the law of mechanical energy. Now the work done by the potential energy. Okay, so let's first work out the work done by, or rather, let's write down what we know. Okay, so let's start with the kinetic energy. The initial kinetic energy equal to 0 because it starts from rest. Okay, it starts from rest. That's why the initial kinetic energy is 0. So we have the initial kinetic energy. We want the final kinetic energy. The change in potential energy, let's check that out. The change in potential energy, final potential energy minus the initial potential energy, is equal to, now let's see what the final potential energy. The final potential energy is going to be 0 because all the potential energy will be converted to kinetic energy due to the law of conservation of energy. So it will be 0, it will be the final potential energy minus the initial potential energy that it had. The initial potential energy would be the mass times the gravitational acceleration times the height.
It's below the horizontal. So a force of 85 newtons at an angle theta, which is 25, right? So this is your trolley, right? And it's being pushed for a distance of 5 meters, right? And the question says find the work done by the shopper on the cut as she moves down a 5. So we're looking for work done, right? So remember that the work done is equals to F force of theta times the distance moved by the force. Okay, so we can call delta x, right?
Just checking
So
something
F
here. It
cos
seems to
theta,
be
we're
acting.
simply resolving that force in the horizontal. Okay, so in our previous tutorials, we were looking at resolving forces. So if you're to resolve that force in the horizontal,
Okay, yes. I was just picking up someone else's teams or colleagues streaming. Okay, now we have the final, the initial rather, the initial potential energy. Remember, potential energy is mass times the gravitational acceleration times the height. Now, in this case, the height would be h that it falls through, okay? Because that would be its initial potential energy. It falls through a height of h, which means its initial potential energy would be mgh. Okay, so 0 minus mgh is just negative mgh. It's the potential energy. So we want kf, we have ki, we have the change in potential energy. What is the force of friction? What is the force of friction? Let's work that out. The force of friction is just going to be, how do we work out friction? It's the kinetic coefficient of friction multiplied by the normal force. Okay, and in this case it will be the kinetic coefficient of friction multiplied by the normal force. In this case would just be the mass of the box times the gravitational acceleration, and we're going to work that out. So now we have all the formulas that we require. Let's work out the answer. Okay, so the change in kinetic energy, I'm going to continue writing down the formulas. So the change in the kinetic energy plus the change in the potential energy, which we've already worked out, plus the work done by the external forces, which is just the force of friction times the height, is equal to 0. Now we've already established that the change in the kinetic energy is going to be the change in the kinetic energy. It starts from rest. Okay, it starts from rest, so the kinetic energy at the end is all that matters. So it'll be a half, excuse me. So the change in the kinetic energy, should have written this for, would be the mass of 1 plus the mass of the ball, the mass of the box plus the mass of the ball times their velocity. They're going to have the same velocity, so they're tied together. Minus, we've already established that the change in the potential energy is m2 gh, right? And then the force of friction, the work done by external force, is mu kinetic times the mass of 2, rather the mass of 1, because each the one going to cause the friction, times the gravitational acceleration, and all of that should be equal to 0. G and all of that should be equal to 0. Okay, now let's fill in everything that we can. Let's fill in all of the blanks. So it's a half times, or rather we want the velocity v here, the velocity at the end this ball is going to have, that velocity we want v. Okay, so let's make v the subject of the formula. So v would be equal to, and you can go and check this, but v is going to be equal to 2 times m1 plus m2 minus mu km1 g Excuse me, I wrote wrong here. If it's equal to 0, you take the both of them over. This is going to become m2 gh plus mu k m1 g. Okay, divide by m1 plus m2, and of course then you multiply by 2 on both sides to get rid of the half, and you find the square root. Because it's v squared, you just want v, so that if you find the square root, it will be to the power of a half, and that is making v the subject of the formula. Now you can actually substitute all that you know in to this little formula. Okay, so we have that all should be to the power of a half. That all should be to the power of a half. Let me, I see it keeps disappearing when I draw it on the screen. Up to that point there, the power of a half, it should be 2. By the way, this 2 should be multiplying with the whole thing, so it should be 2 multiplied by, what's the mass of 2? It is 5, it's the block, m2, multiplied by 9,8, which is g, multiplied by h, which in this case is 1.5. 2 should be multiplied by that whole thing minus mu is 0.4 times, or multiplies rather, same thing, 3, which is the block of m1, the mass of m1, multiplied by g, which is 9,8. Okay, I know I'm writing a bit illegible, and then m1 plus m2 is nothing but 3 plus 5, which is 8. And if you were to work this out, you would find that the speed at the end is 3,74 meters per second. Okay, I hope when you do this that you actually understand what is happening, and that is the correct answer. And you can actually go and see that there they give it as 3.74 meters per second is the correct answer. Now onwards to our next question. Question 7. So question 7 tells us the following. An 820 Newton marine in basic training climbs a 12-meter vertical rope. So this marine is climbing up a rope at a constant speed in 8 seconds. Okay, what is his power output? Okay, so first we need to calculate how much work is being done by this marine. Now we know that work is equal to force times distance. Okay, force times distance. Now what is the force that is overcoming? Since he is not accelerating, okay, the force, because he's climbing at a constant speed, it's not accelerating, so there's no net force, which means that the force that he's climbing, that he's exerting, is exactly equal to the gravitational force. Since he is not accelerating upwards, he's climbing at a constant speed, he's not accelerating or decelerating. Okay, so he's climbing at a constant force, and that constant force is the one that is exactly equal to gravitational acceleration. So for him to be climbing at a constant speed, he must be climbing with the same force as gravitational acceleration. So the force of gravity on him is 820 newtons, which is his weight. And then multiplied by the distance he climbs up a 12-meter vertical rope. 12 meters he climbs up. That gives you the work of 9,840 joules of work. This is the amount of work he does. 9,840 joules of work. Okay. Now, what is his power output? What is power? Okay. Power is the work per unit time. Okay. In this case, it will be the work of 9,840 joules divided by 8 seconds, and that gives you a power output of 1,23 kilowatts. Okay. That is his power output. This is the amount of power he puts out per second. Okay, that's the amount of power he puts out in every second. On to our next question. Okay, so this is a pretty basic problem. Okay, we first had to calculate how much work is being done by this marine, and then divide that by the amount of time over which this total amount of work is being generated. That will give you your power output for that period. Okay. Question number 8. Question number 8. Okay. We have a 10 kilogram block that is sitting on a horizontal surface. Okay, so a 10 kilogram block is sitting on a horizontal surface. Okay. And this horizontal surface is frictionless. And this block is attached to a light spring. Okay, so let's try and draw. So we have a 10 kilogram block on a horizontal frictionless surface. Okay, we have a 10 kilogram block, That's 10 kilos. And it is attached to this block is attached to a spring. Okay, so this block is attached to a spring, to a light spring which has a force constant. So the force constant for the spring K is equal to 0.8 kilonewtons, or rather, let me just write it in 0.8 kilonewtons is just 800 newton per meter. 800 newtons per meter, that's the spring constant. Then they tell us that the block is initially at rest at its equilibrium position when a force of magnitude, so the force P has a magnitude of 80 newtons, and this force is acting parallel to the surface and is applied to the block as is shown. So the force of P is parallel to the surface and it pushes against the block, or pulls rather. So let's say force P pulls the block, okay, from its equilibrium position. What is the speed of the block when it's 13 centimeters from its equilibrium position? Okay, so the block is being pulled from its equilibrium position, or it can be pushed from the equilibrium position. What would be its speed? Let's work that out. Now the energy, the total mechanical energy, is equal to the potential energy, which in this case is the spring potential energy, a half kx squared, plus the kinetic energy, k, or rather m v squared. That is the potential energy, the kinetic energy. Now we know that the energy, the mechanical energy, or energy in general, is the capacity to do work. So energy can be written as the capacity to do work, a half kx squared plus a half mv squared. Then we have that the force, we know that work is equal to force times distance. Force times distance. That's a half kx squared plus a half mv squared. Okay? So the sum of the kinetic energy and the potential energy, which is the spring potential energy, would be equal to the work done by this force. Now, if we were to fill in all the values that we have so far, we know that this force P is just 80 newtons. I'm not going to put in the values. It is being stretched or compressed about 0.13 meters. Let me see, 0.13 meters. Okay. Then we have a half times the spring constant, which is 800 newtons per meter. Okay, I'm not going to write in those values. The distance, it's 0.13 squared. Don't forget to square. Added to that is a half times the mass, which in this case is 10 kilograms. I see it's barely fitting in the screen there. Plus a half times 10, and then v squared, which is what we want. We want v. Now if you were to work out v, let me rewrite it. 80, that is 0.13. 80 times 0.13 is 3.6 3.64, 3.64, or rather it is 80.36, should be 10.4, 10.4, which is equal to this 0.13 times 800 times a half, should be 6.76. Of course, this is in Newton per meter. If you were to put the units in, plus 5 kilograms, because a half times 10 is 5. You write it in meter. It's 5 kilograms multiplied by V squared. Okay. You can now solve for V. Okay, subtract 10.5 minus 6.74 and divide it by 5. You have that V squared is equal to 0.728 meters squared per second squared. That is V squared. Okay, so just a V squared, just a recap, V squared is equal to 0.728 meters squared over second squared. Okay, if you were to find the square root, your answer would be in meters per second, and the square root of 0.7 is just 0.853. Okay, 0.853. So that would be your answer. 0.853 would be the force or the speed when the block is 13 centimeters from its equilibrium position. Okay, let's see if that's an option. 0.85, there it is. Let's check it. That was question number 8. And yes, it is, the correct answer is 0.85 meters per second. We are correct. Now question number 9. An interesting question. Okay. And I hope that you pay attention to this particular question, because lecturers tend to ask questions like these. Okay. Two clowns are launched from the same spring-loaded circus cannon. Okay, so two clowns with the spring compressed the same distance each time. Okay, clown A has a 40 kilogram mass while clown B has a 60 kilogram mass. What is the relation between their speeds at the instant of launch? Okay, so let's say the potential energy, we know that potential energy is equal to, from a spring, is a half kx squared, while the kinetic energy would be a half mv squared. Okay, now if we were to let, since this is conservation of energy, if we were to let the potential energy all be converted to the kinetic energy, okay, for each clown, this is for each clown, for each clown, clown A and clown B, we will have that a half kx squared, the potential energy, is equal to a half mv for clown A squared, and then the same thing for clown B, a half kx squared equal to a half mv b squared. Okay, that would be because we've equated the potential energy equal to the kinetic energy for each clown. This is for clown A and this is for clown B. Let's just say that the mass of clown A and the mass of clown B. So now we have this formula. Okay, now since both of these clowns are launched from the same spring, and they are compressed the same distance, these two, the spring potential energy for both of them is exactly the same. So we can equate that a half ma va squared is equal to a half mb vb squared, since the kinetic energy, since it's the same spring being used by both of them, they will have exactly the same values for this part. They will have the same value here and the same value. If this one is 50, then this one will also be 50. And then we can equate their kinetic energies. Now, if we equate their kinetic energies, okay, if we were to equate their kinetic energy, a half ma, velocity of a squared, equal to a half mb, velocity of b squared, we have that the halves cancel. We have that ma, which is 40 kilograms times va squared, and mb, which is 60 kilograms times vb squared. We have that if we take it over 40 over 60, just leave it as 40 over 60, and vb over va, both squared. Okay, now this is nothing but 2 over 3. Square root of that is equal to vb over va. Therefore, the relationship between va and vb is that vb is equal to the square root of 2 over 3 times va. That is what vb is. Okay, so va is not equal to vb, and the rest of them, it doesn't show up. So this is what the relationship between va and vb. Finally, question number 10. Question number 10. We check something quickly. So finally, let's check question number 10. A 10 kilogram block, this is question number 10. A 10 kilogram block is released from rest at the top of a frictionless incline. Okay, so we have an incline. Let's just write down. So a 10 kilogram block is released from rest at the top of a frictionless incline. Let's draw the situation. We have an incline. We don't know what this angle is yet of the inclination. We have a block which started at rest. It's not a 10 kilogram block, it's a 1 kilogram block, and it makes an angle of 37 degrees with the horizontal. An unknown distance down the incline from the point of release, there's a spring. So there's some distance until it hits let's say it hits here, a spring. There's a spring here. So there's an unknown distance from here to this spring. And the spring constant of that spring is equal to 200 newtons per meter. Now it is observed that the mass is brought momentarily to rest after compressing the spring for about 10.2 meters. So it compresses the spring. It compresses the spring for about 0.2 meters. Now they want to know how far in total does this mass slide from the point of release until it's brought to rest inside the spring or on the spring. Okay, so first of all, we need to calculate the force that is making this block slide down. So the force, the parallel force, okay? The parallel force, if you were to do inclination vectors, okay, you would see, let's just draw it. If you were to draw the incline itself, okay, let's say the box is there. Draw from the center of the box, straight down. Then we'd have this one, and then of course here. Okay? This would be F normal, this would be F perpendicular, and this would be F parallel. Okay? Now F parallel is the force, this is the weight, and this is the parallel force, the normal force or the perpendicular force, and the parallel force will give you the weight, or the hypotenuse in this case, which is, this is the weight. Going straight down. Now, how do we calculate the parallel force? Okay, that angle there would be 37 degrees. It's theta, 37 degrees. How do we calculate? The sine of theta times the weight. Okay, so that's how you calculate the parallel force. So the parallel force is equal to the weight of the box times the sine of theta. And in this case, the weight is the mass times the gravitational acceleration times the sine of 37 degrees, which is in this case. Now the mass of the block is 1 kilogram, 1 kilogram, 9,81 is meters per second is the acceleration, and then the sine of 37 degrees. That is your parallel force. So you have your parallel force, which is 5,89 Newton. So you've calculated the parallel force. Now pulling the block down. Okay, now how much work is done by this force pulling the block down? How much work is done by this parallel force? Okay, so the work by this parallel force, we want to know how much work it does. Okay, because the work it does is going to be equal to, the work done by the parallel force is going to be equal to, excuse me, the parallel force itself multiplied by the distance. And this is the distance that we want. This is d, this distance we want. Okay, so that's the distance we want. But first, before we can get there, let's calculate how much energy or potential energy is stored in the spring due to the block when it hits the spring. Okay, so the potential energy in the spring we know is equal to a half kx squared, where x is the compressive distance. Okay, so it's going to be a half, the spring constant is 200, remember, newtons per meter, while the compressive distance, in this case it's being compressed by 0.2 meters, we square that, just compressive distance, we square 0.2 squared 200 Newton meters times 0.2 squared. Okay, that gives you 4 joules. So this block imparts 4 joules of energy to the spring. Now, in order for it to impart 4 joules of energy, since it started from rest, it had 0 energy initially. Okay, but then it gained energy due to the parallel force. Okay, and this energy was transferred to the spring. Okay, so now we know, since no energy was lost, it's a frictionless surface, they tell us. It's a frictionless incline, so no energy is lost. So all its energy that it gained, so all the work that was done, so all the work done by the parallel force is equal to the work given to the spring, imparted to the spring. Okay, and that is just equal to 4 joules, as we just worked out. Now, what is the work done by the parallel force? That's just the force, the parallel force times the distance, and we have that the parallel force is nothing but, we've worked it out as 5,89 times this distance which we want. We have 4 joules. Therefore, the distance that this block travels before it comes to rest is equal to 0.68 meters. That's the distance that this block travels before it comes to a stop in the spring. And that, ladies and gentlemen, we can check then, 0.68 meters. Let's check. Yes, the correct answer is 0.68 meters. Okay, that is all that we have time for today. I hope you enjoy and that you understand what we did. Enjoy the rest of your day, and I will see you next week.